Hello there. In this video, we're going to talk about the second derivative in multivariable and hopefully maybe get more of an understanding about why, like in our first video, how come it is when we're looking for a relative maximum or minimum, we only have to worry about the first set of partials with respect to x. Why don't we have to worry about the partials with respect to y? How come when we're looking for a saddle point, we only have to worry about if d is negative? So we're going to talk a little bit about those, and hopefully this will clear a few things up for you if you have trouble with it. So our first thing we'll look at is the derivative itself. Remember, this is a little bit above our pay grade to understand. We're not quite ready for that just yet. But we can talk about this. The second derivative rule says we're going to take the second partials with respect to x, multiplied by the second partials with respect to y, minus the partials of xy squared. Now, so let's talk about one thing first. Let's say if d is positive. Let's say d is positive. D is greater than 0. Well, if d is greater than 0, and we also know, this is an if right here, and we also know that this is always going to be a positive number. These are always both going to be greater than 0. Remember, this one again is an if. Let's say it is positive. Well, if I know that this is positive and I know this is going to be positive, I can rewrite my second derivative as follows. Equals d plus fxy squared equals fxx times fyy. Now, remember, this is going to be a positive value. This is going to be positive. We know that by our definition. So if this is positive, this rule over here also has to be greater than 0. So that's going to be our rule right there, that this product has to be greater than 0. So let's talk about the two conditions. One, what if f of x was positive? Well, if the second partial with respect to x is positive, remember, I still have to keep this positive. If I let this be negative, this is no longer going to be a true statement. If this is less than 0, that's going to make that a not true statement, so that can't happen. So the only way this can happen is if both are positive. The only way that's still going to be true is if both are positive. So if my second partial with respect to x is positive, then my second partial with respect to y also has to be positive. Well, let's think about that, what that means graphically at our critical point. Remember, these are only our critical points. So let me see if I can draw this in 3 dimensions instead here. There we go. If I'm at my critical point, well, my partial with respect to x is going to be positive. So it's going to be concave up. My partial with respect to the y direction is also going to be concave up. Remember, we are at we've already established these are critical points. So since both directions are concave up, this has to be a relative minimum. So remember, they're both concave up. That's what this is kind of saying right there. And that is why we only have to worry about the second partial with respect to x, because the second partial with respect to y would also have to be greater than 0 if d is positive. That's the big condition right there, if d is positive. Well, what about my other condition? What if the second partial of x is less than 0? Well, if this is less than 0, this is now negative times a positive. Well, that's not going to be greater than 0. So the only way this will still be a true statement is if the second partial with respect to y is also less than 0. So in this case, well, let's take a look at what's happening. Here, in the x direction, we're now concave down, and in the y direction, we're also concave down. So if we look at our critical point, here's my critical point. In the x direction, we know we're concave down. And in the y direction, we're going to be concave down. So this has to be a relative maximum. And that is, again, why we only have to worry about the second partial with respect to x. Because the only way that will still be true if d is positive is if fyy is also less than 0. So that takes care of the relative max and mins. What about the saddle point? Well, from BC calculus, we learned if the second derivative is positive, then we have a relative minimum. If the second derivative is less than 0, we have a relative maximum. So we talk about different signs right here. One would be concave up, and the other is concave down. So the question we want to ask is, what if fxx and fyy have opposite or different signs? Well, think about what happens here. One would be concave up and the other would be concave down. So if I try drawing that, here's my critical point. Let's say fxx was positive, so in the x direction we're heading up. And let's say fyy was negative, so this is concave up, this would be concave down. And we get a function like this. Now if you notice, this kind of looks like our hyperbolic paraboloid. You kind of think like that. Like, this is the hyperbolic paraboloid at that center, where one part's concave up and the other part's concave down. And therefore, at this critical number here, we have a saddle. But what does that do to my function? Well, remember, my second derivative is fxx fyy minus the partial of fxy squared. Well, if this is positive and this is negative, minus a positive here, that's going to be less than 0. If this is negative and this is positive, it's still minus a positive. That's also going to be less than 0. So in either case, it doesn't depend on the second of xy, it just depends on fxx, fxy. If they are opposite signs, d would be less than 0. And that's our rule right here. If d is less than 0, we have a saddle point. One of them has to be, they have to be both opposite signs right there. All right, so that's the end of this video right here. Go on to the next video, and we're going to take a look at a bunch of examples. See you then.